One last problem, and it breaks everything we just built. What is the probability that a standard normal exceeds 4? The answer is about 3 times 10 to the minus 5. Small, but perfectly real. Estimate it by the method of last lesson. Draw 10,000 samples, count how many exceed 4. The expected count is 1/3 of a single sample. So in a typical run, none of them do, and Monte Carlo confidently reports that the probability is 0. The problem is not the averaging, it is where we sampled from. Almost every draw landed in a region where the quantity we care about is exactly 0, and contributed nothing at all. So sample somewhere better. The algebra is one line. The integral of h times p equals the integral of h times p over q times q for any density q you care to choose. So the expectation under p is the expectation under q of h times the ratio p over q. That ratio is the weight. It corrects for having deliberately sampled from the wrong distribution, and the estimator stays unbiased for every valid q. Compare that with rejection sampling, which through mismatched draws away. Important sampling keeps all of them and reweights instead. Back to the tail. Choose Q to be a normal centered at 4 instead of at 0. Now about half of every sample lands in the region we actually care about, rather than 1 in 30,000. Each of those samples is wildly overrepresented, so the weight cuts it back down. Here the weight is e to the 8 minus 4x, which is minuscule out in the tail, and that shrinking is exactly what turns a pile of hits back into the correct, tiny probability. The numbers. With 10,000 samples, plain Monte Carlo has a relative error of about 180%, worse than useless. Important sampling, with the very same 10,000 samples, gets about 2%. The variance falls by a factor of roughly 7,000. So which Q? In principle, there is a best one. Q, proportional to the absolute value of h, times p. It gives literally 0 variance. And it is unusable, because the constant that normalizes it is the integral you were trying to compute in the first place. It still tells you what to aim for. Put your samples where h times p is large. Here is the variance as you slide the proposal center from 0 out to 8. At 0, it is plain Monte Carlo. The minimum sits near 4.1, 4 orders of magnitude below, and the valley is broad, so you do not have to hit it exactly. And there is a way to lose badly. If Q has lighter tails than P, then P over Q blows up out, where Q has almost no mass. A single freak sample dominates the entire average, and the variance can be infinite. The rule of thumb: your proposal should be heavier-tailed than your target, never lighter. Important sampling. Draw from Q instead of P, and weight each draw by P over Q. Unbiased for any valid Q, and a good Q cuts the variance by orders of magnitude, which is the only lever the 1 over root n rate ever leaves you. That completes Monte Carlo, and with it, the course. 65 lessons. From sample spaces and counting, through random variables, estimation, testing and regression, into Bayesian inference, stochastic processes, measure theory, information theory, and finally simulation. It began with the axioms of probability on a handful of outcomes. It ends with algorithms that compute integrals nobody can do by hand, in spaces nobody can picture. The same subject, all the way through. Thank you for watching.